Welcome to my talk on the hidden rules of world-class C++ code. My name is Boris Schäling, and as you probably have guessed, I'm a C++ programmer. I work in the electronic trading industry, which means I use C++ to create computer programs which are connected to exchanges around the world and to a large extent buy and sell stuff at exchanges automatically. A lot of people find it weird when they hear that first, but what these computer programs do in the end, they try to buy stuff for a low price and sell it for a high price. In that industry, a lot of C++ is used as the industry is very competitive and performance matters a lot. So that's a part of my life where I get a lot of C++ experience from. When I'm not working on automated trading systems, I can also be found in the Boost C++ community. That is the open source organization responsible for developing and maintaining the Boost C++ libraries. And if you are a C++ programmer, I know I don't need to tell you what the Boost C++ libraries are. I don't know whether you have been to a lot of conferences. I've been to a lot of C++ conferences. And usually you find a lot of talks where people introduce a specific language feature to you, or where they talk about a library and try to explain you how to use that library. In fact, that is something I did myself very often. I went to a lot of conferences and introduced a lot of Boost libraries to the audience. So for this conference, I thought I'd pick a different topic, because when I look at all these talks you usually find at C++ conferences with all those different topics, they have one thing in common, and that is making people better developers. And an important aspect of being a better developer is, of course, being able to write better code, awesome code, maybe world-class code. So I thought for this conference it's maybe a good idea to talk about this end goal. Not about a language feature or about a library. All that knowledge, of course, helps to become a better developer. But maybe let's talk about world-class C++ code. That can be sometimes a bit difficult to define what is actually world-class C++ code. It can be also a controversial topic. Discussions can get somewhat heated. So throughout my talk, I'm trying to stay calm and look like the guy on the left side. If you object to anything I say, and you have a different point of view, and you become a bit aggressive, and you look like the guy on the right side, that's fine with me. I don't have a problem with that. So the hidden rules of world-class C++ code, it maybe also sounds like as if I'm standing here and claim I'm the world's best C++ programmer. I think there's no one who would ever claim that. I could work with a lot of C++ programmers who have a lot of experience and who wrote code where when I looked at that code, I said to myself, wow, that code is really good. There's something special about that code. That code is better than the average code I maybe come across. So that made me think about what is so special about that code. So being in the electronic trading industry, being involved in open source organizations helps you, of course, to work together with all those smart people. And in this talk, I'm trying to pass on that knowledge a little bit of what I learned. So my entire talk revolves around the factory method pattern. I picked a design pattern I believe most of you are familiar with. Even if you're not familiar with this design pattern, I think it's a very easy one which you can understand on the spot. So all the other slides which are following this slides are somehow revolving around this example. So it's good to remember this slide. So what does the factory method pattern look like? If you Google for the factory method pattern, you find thousands of websites where people explain to you what this design pattern is about. And I created here a UML class diagram which you find similarly on the internet on thousands of websites. So all these UML class diagrams for this design pattern look more or less the same. Actually, if you go to Wikipedia, you find something which looks really, really similar to this one. So what did I do here? In this factory method pattern, I have two class hierarchies. A class hierarchy here on the left side with 3 classes, and a class hierarchy on the right side with 3 classes. There's a base class called connection, and the other class hierarchy has a base class called connection factory. Both of these base classes have one method. A connection can be used to send something through that connection, and a connection factory can be used to make something. What does a connection factory make? Well, obviously, it makes connections. Connection and connection factory are abstract classes. You can see that because connection and connection factory, the font style is italic, so we cannot instantiate these classes. We cannot have an object of type connection or an object of type connection factory. But as these are base classes, we can derive other classes from them. And this is what I've done here. So connection has 2 classes derived from them, from connection. That is TCP connection and UDP connection. And there are 2 other classes derived from the connection factory called TCP connection factory and UDP connection factory. And how that obviously works is that if you have a TCP connection factory instantiated in your program and you call make on that TCP connection factory, well, you get a TCP connection. And if you have a UDP connection factory instantiated on your program and you call make, you obviously get a UDP connection. That's all we need to know to understand the factory method pattern for this talk. Make sure that you keep this in mind because all the source code we are going to see on the following slides, they are all somewhat based on this UML class diagram. Now, before I jump into C++ code, let's step back and think for a moment about when you would want to use this design pattern. So again, I went to the internet and looked a little bit around what other people say, and found some random websites and tried to understand what do other people say, why do I want to use this design pattern in my applications. So what did the first guy say? He wrote somewhere that places that need an implementation of the connection I put in there, the other guys of course had other examples, they do not need to know how to construct one. All right, what does it mean? If I need a connection somewhere in my code, and it is maybe really complicated to create a connection because a lot of code needs to be written to actually provide a TCP connection to your program, then if you use the factory method pattern, you don't need to worry about how complicated it is to create a connection because all you need to do is call make. If you have a factory and you call make, it doesn't matter how much is happening in make. Make gives you the connection you want and you're happy. True. That's a nice benefit this design pattern gives you. Agreed. That's something which is great about this design pattern, and that is one of the reasons why we might want to use this design pattern. What else is there? Another guy wrote, this design pattern provides a simple way of extending the family of connections with minor changes in application. All right, what does that mean now again? It means that we can easily extend our program. If you think of the class hierarchies we have with the base classes and the classes derived from them, it's easy to add another class later. So right now we have maybe only a TCP connection and a UDP connection, but next week we want to have another connection. No problem, add just as many connections as you want. The existing program with all the established code doesn't need to be changed. So this bullet point here is about extensibility. Also great. Nice that this design pattern provides us extensibility. What is the next guy saying? You can delegate to a subclass the creation of a connection that can vary based on application needs. All right, what does that mean again? It's somewhat linked to this one, while this bullet point was about talking extensibility when it comes to connection. This guy here talks about the extensibility when it comes to the connection factory. It's somewhat linked to each other because if you have multiple connections, you probably have multiple connection factories. Just as we have seen, you have one TCP connection factory for one TCP connection class. you obviously have one UDP connection factory for one UDP connection class. So if you add another connection type, you will probably also add another connection factory. And it's again true, it's very easy to extend your program if you are using this design pattern. And let's look at another comment from another guy. He wrote, it allows a connection to be requested without inextricable coupling to the act of creation. All right, what does that mean? It means that when you have a connection factory and you call make, the connection factory doesn't need to create the connection when you call make. Because the connection factory was created before, it maybe created already a couple of connections and cached them, and later when somebody calls make, it provides you one of the previously created connections. As the connection factory is a class, it can have state, so when you instantiate a connection factory, it can already do stuff which could be useful to provide you a connection later faster when you call make. For example. So it's true, all of these bullet points are good reasons why we want to use maybe this design pattern. Now let's look at a traditional implementation, how we would write something like this in C++ code. Well, it's not that hard. We have seen before in the UML class diagram that we have 6 classes, 2 base classes, the other 4 classes derived from the 2 base classes. That's easy to define in C++. So here on the left side, I have my connection class hierarchy, connection base class, TCP connection, and UDP connection derived from the base class. I have my send function. Here it is pure virtual, which makes the connection class an abstract class. Here I have send defined and implemented. For my examples, I'm obviously not creating real TCP or UDP connection. When somebody calls send later, I'm just writing whatever is passed to standard cout. The base class has a virtual destructor, as it should be when you work with virtual member functions. I think that is all rather easy to understand C++ code. And on the right side, you have the class hierarchy for the connection factories, and they kind of look the same. What's maybe important to note here that the connection factories return a connection. Because we are using a class hierarchy, the make function here on the right side returns a pointer to a connection, so that the derived classes like TCP connection factory and UDP connection factory can return through that pointer to the base class, for example, a TCP connection or a UDP connection. I think I don't need to explain much about this code because this is really good old traditional C++ code, as maybe some people have written already back in the 1990s. So how would you use now this design pattern? Here I have defined a send function, which you can pass a connection factory to. The send function would call make on the connection factory to get a connection. And then it would call send on the connection to just send some random data through that connection. And as we have seen, as make creates an object with new, we have to make sure that we delete this object again, otherwise we have a memory leak. Now here I have my main function where I can make use of my send function, and in this very simple sample program, I just check whether somebody invokes my sample program with a command line option. So if you compile this code and you run it, and you pass TCP as the one and only command line option, then I create a TCP connection factory. If somebody starts that program and doesn't pass a command line option, or maybe the command line option UDP, I create a UDP connection factory. And no matter which connection factory I create, I can pass it on to send, and send can do its work. So here everything comes together, what we were just talking about when we were looking at the explanations why we would want to use this design pattern. So this is extensible. We can reuse the code here. We don't need to change the code if somebody wants to introduce some more connection or connection factories. So this provides us here all the advantages we want to see when this design pattern is put in use. Of course, as also the connection factors are created with new, I shouldn't forget to delete them again, otherwise I have a memory leak. It's maybe also important, but I guess it's also somewhat obvious. No matter which connection factory I instantiate, the pointer can have a different type. It doesn't need to have the type TCP connection factory or UDP connection factory. The pointer here has the type connection factory, the base class. I guess all pretty standard C++ code. So looks like we are done for the talk, but not yet. So, oops. The first thing which we notice is that we have all these new and deletes all over the place. So if you are somewhat familiar with what we have been working on in C++ in the last few years, then you are maybe familiar with the term modern C++. When we think of modern C++, we think, among others, of not using new and delete ourselves. So what do we use instead of new and delete? We use smart pointers. So when you use new and delete yourself, you maybe have experienced this yourself, that when you create an object somewhere in your code with new, you need to remember that somewhere you have to call delete again, and if your functions get very long and you think of so many other things, it could easily be that you forget to call delete. Or maybe there is some code between new and delete. You didn't forget to write delete, but maybe there's some code between new and delete which throws an exception. So even though you wrote delete, it could be that this line is skipped because an exception is thrown somewhere before. So these are reasons why we don't do this anymore in modern C++ and why we use smart pointers. So let's revise this traditional implementation with smart pointers. So this is now the modern C++ implementation where the make functions of the connection factories don't return a raw pointer to a connection anymore. They return, for example, a std unique pointer of a connection. So how do I need to change the send function in the main function? Well, obviously, I use now also here the std unique pointers. After all, this is what I get from make. Of course, I also use a std unique pointer here now. I use my helper function from the C++ standard library, std make unique. And when I use that program now with the unique pointers, I don't need to worry about a delete anymore. Right? When the unique pointers go out of scope, when, for example, this function returns, this unique pointer is destroyed, and the destructor of that unique pointer will delete the connection object. All right, great. This is modern C++. You want to be modern, that's good. Are we now done with the talk? Not necessarily. As Captain Jean-Luc Picard from the USS Enterprise says, there is quite a lot of boilerplate code. And it's true, we could simplify this code a lot. After all what we need in this program is either a TCP connection or a UDP connection, and not all the other classes around it. So how do we do this without a design pattern? So this is now the entire program on one slide without using the factory method pattern. I have now only two classes, a TCP connection and a UDP connection. They still provide a send function. I don't have a base class. I don't have any factories. I'm just instantiating one of the two classes depending on the command line option, which I detect. So when the program is invoked with TCP, I just instantiate my TCP connection and send hello. Otherwise, I instantiate my UDP connection. There's no doubt that this code is much shorter. There are less classes used. It's probably easier to understand what's going on. I don't need to worry about some design pattern. But that's, of course, not the point of this talk. So this talk is about how to express the factory method pattern with world-class C++ code, not how to forget about the design pattern and do something else. So yeah, it's true. It's better if we can write something like this. And if you, again, Google on the internet the design pattern, a lot of people also say, if you don't need to use the design pattern, if you can express what you want to express without the design pattern, then go for it. But if you might need to use the design pattern, the question is, how do we express this design pattern now in code which we believe is good, awesome, world-class? So let's forget about this solution because, yeah, there is no design pattern. Let's go back to C++ code based on the factory method pattern. Before I go back to C++ code, let's think again about it, what the advantages of this design pattern are and how we could express these advantages in C++ code. So let's try to break down this design pattern. You have seen the other slide before where I put some quotes from some random people on the internet on. What were other people saying why we want to use the design pattern? So let's go again through all of these bullet points, but think about how this relates to the C++ features we find in the programming language. So for example, somebody said that if you have this design pattern, it's relatively easy to create objects because you just call that make function and you get what you need. You don't need to worry about how complicated it is maybe to actually create a connection. And that's true. So we can easily delegate the object creation to a factory method. No doubt. But that's actually something every function provides us, right? If all you need to do is put a lot of complicated code of how to create a connection somewhere else so that you can provide it in an easy way to someone, you don't need to use this design pattern. You just put all of this code in a function, call it, for example, make TCP connection or make UDP connection, and someone else is happy. Someone else just needs to call that function and gets the connection he needs. So when it comes to this advantage of the design pattern, and if it was only this advantage, if that was the only reason you were using this design pattern, then you don't really need it because all you need is a function. Now, some other guy, or actually several people on the internet claimed that if you use this design pattern, that it is very easy to extend it. And it is true, you can easily add new connection types, you can easily add new connection factories, there's no doubt. But let's think about what we just said. Let's say you have a function, make TCP connection, and another function, make UDP connection. Well, that's also easy to extend. You can always easily add functions to your program without having to change the other functions which you had written before. So, yeah, when it comes to functions, there's no question that you can easily extend your program by adding more functions. So, extensibility, yes, that is something that the design pattern provides, but so far it seems that all I need is functions. Well, we have seen that we can also easily reuse code thanks to runtime polymorphism. We have seen that the send function can be used with TCP connections, UDP connections. If you add some more connection types or some more connection factories next week, it's no problem. The send function can stay as it is. Everything will just work thanks to runtime polymorphism. But there we have something else in C++, which we are very proud of. That is templates, right? If it comes to code reuse, you don't need to use runtime polymorphism in C++. You can just turn to templates. So if you just think about what we went through, we have functions, we have templates. So if all you need is extensibility, delegation, code reuse, you don't need that traditional implementation of the design pattern. So far, you just need functions and, yeah, maybe some templates. But there's more. The factory method pattern also allows us, we mentioned this before, to do some stuff when a factory is created, so that when somebody calls make later, that maybe less has to be done. Right? Factories can have a state. So when a factory is created, I said it before, it could, for example, pre-allocate some connections, and when somebody calls make later, it gives you immediately a connection it created before. That is something we can't really do with a function, right? When we call a function, the function will just execute all the code, but the function cannot pre-allocate something before it's even called. So, indeed, maybe we have to do something different if we want to have that benefit also with an alternative implementation in C++. So what we can actually do here, we can use classes a little bit like the factory classes we have seen. So we can instantiate something so that the constructor in the class has a chance, for example, to create connections in advance. And then later we can go to the instance of that class, call make, and get a connection faster. So maybe it's something where we have to introduce classes again, but so far no reason for inheritance. So we could have a TCP connection factory, we could have a UDP connection factory, but there doesn't need to be any common base class so far. So, oops, I skipped one slide. Decoupling is, the presentation decided to skip its own slide. There should have been one more slide, and that is that there's one more thing you can do with the traditional implementation of the design pattern. And that is, if you have now various objects of connection factories, and all these objects are based on a different type, you can take, of course, the addresses of all these objects and store them in the same variable as long as this variable has the base class as its type. So I mentioned this also before in a slide. If we have a connection factory pointer variable, we can put the address of a TCP connection factory or of a UDP connection factory in that variable, and that all works. So that is a reason where you would need to have a class hierarchy with a common base class. If you have TCP connection factory and UDP connection factory as unrelated types, you can't really take a TCP connection factory and put it in a variable and later put a UDP connection factory in the same variable. It obviously doesn't work. Or does it? We will see. So now let's go through the points I just made, and let's look at the C++ code, how we would now implement this. We said that it seems that all we need is actually functions. If we just want to delegate the creation of connections to somewhere else, well, just create functions. We don't need some traditional implementation of the design pattern. So I have now here a make TCP connection function and a make UDP connection function. And the make TCP connection function returns a TCP connection, make UDP connection returns a UDP connection. So I still have, of course, my TCP connection and UDP connection classes. So I still need to represent connection type somehow. But yeah, I have now all these functions. How do I use them? I have again my send function here on the right side and my main function. And I also said before that if we want to make sure that we can reuse code, no matter what connection types and what connection factories we use, then we can just turn to templates in C++. So my send function is now a templated function. It takes any connection factory. It will call the connection factory as if it is a function, which is nice because in my case the connection factories are functions. The connection factory in my send function returns a connection. I use here the auto keyword, which is then either a TCP connection or a UDP connection. Then I call send. Now in my main program, I again evaluate the command line option. If somebody starts the program with the command line option TCP, I just pass make TCP connection, the function make TCP connection as my connection factory to send. Otherwise, I pass make UDP connection to send. All right, that all works. So what do I get now? I get the delegation. I can just call a factory and get the connection, no matter how complicated it would be in practice to create these connections. So it's easy to get a connection. Delegation accomplished. I have also the extensibility. I can add another function if I want to, make whatever else connection. I have also code reuse. My send function looks like I can use it with no matter how many connections and connection factories I add here. So far, so good. So what I can't do yet with the functions, as we said before, is I can't create yet a connection factory and let it do something before I actually request a connection from that factory. That is where we said, okay, we have to turn actually to classes again. So if that is something we need in our program, if we want, as I said, to provide the connection factories a chance to pre-allocate connections, for example, I just turn to a class. So I highlighted the parts I just changed. I don't have these functions anymore like make TCP connection and make UDP connection. I have now my TCP connection factory class again and my UDP connection factory class. They both provide me again a make member function. They return the appropriate connection objects. What again matters compared to the traditional implementation, these two classes are not derived from a common base class. That is something I don't need so far. So if I introduce now these connection factories as classes, what do I have to change in the rest of my program? The send function needs now obviously to call make on the connection factory, which is passed in there. And down here, I have to instantiate the connection factory before I can actually pass the object as a parameter to send. So again, why did I just change the program? So far we said with the make TCP and make UDP function, everything is working fine. But if I want to have the opportunity to do something in advance when a connection factory is created, then I need a class so that I can do whatever I want to do in advance in the constructor. And later, when I want to access the connection factory and call make, that maybe that factory can provide me a connection faster. That is a requirement I have. Then I have a good reason to not use connection factory functions, but connection factory as classes. Before I come to the next slide, I'm going to change my connection factory classes slightly without telling you yet why. I had just implemented two make functions in my two connection factories. So the TCP connection factory had a function called make, and the UDP connection factory had a function called make. I'm now changing these functions. They are not called make anymore. They are now overloaded function operators. That means I can call the connection factory as if it is a function. That was something I had actually already before when I had my make TCP connection function and my make UDP connection function. I was also calling the connection factory like this, as if it is a function. After all, these were functions before. So if I don't use make functions, but if I overload the function operator, I can have again the same code as I had before in send. Why I changed now my connection factory to this, you will see in the next two slides. Before I continue, I have to do one more thing, and that is I have to introduce again my base class for my connections. So where I'm trying to get it is I want to use my connection factories and I want to be able to store these objects of different types potentially in the same variable again. That leads back to what I said before. When you have a pointer to a TCP connection factory and a pointer to a UDP connection factory, you can store these addresses in one variable if these two connection factories have the same base class. That is something we have seen on a previous slide. So now I'm trying to get again somewhere there, but without having to introduce a base class. So my TCP connection factory and my UDP connection factory, they both still have the function operator overloaded. And now I'm kind of harmonizing the code. The TCP connection factory doesn't return a TCP connection anymore, and the UDP connection factory doesn't return a UDP connection anymore. Both overloaded operators return now a std unique pointer to a connection. So that means that for that part of my code, I introduce temporarily a base class again. So TCP connection and UDP connection are again derived from connection. But for the right part of the code, and that's now the part I want to concentrate on, I don't have a base class. So TCP connection factory and UDP connection factory are still two completely separate types. Now the question is, can I still create an object of TCP connection factory and put it into a variable? And can I then later in my program create an object of the UDP connection factory and put it in the variable? Obviously overwriting what I put in there before. But if I want to do that, how do I do that? What has to be the type of that one variable? Easy to do with a base class, but can it be done with that? Turns out it can. We actually have something in the C++ standard library which is std function. And with std function I can define a variable, which means I can put something into the variable as long as this something has this signature. So here I have a variable called factory defined, and factory can store anything which can be invoked that way. So this is the signature of a function which has no parameters, that's why there are the empty params, and which returns a unique pointer of a connection. And if you think back what I just did in the previous slide, I can go back again. I just changed my TCP connection factory and my UDP connection factory in a way that these classes provide this overloaded function operator. So the signatures of these two connection factories match with what my factory variable here expects. And that's great. Now I can again write similar code as I had done before when I was working with the traditional implementation. I can now evaluate the command line option, and if I detect that somebody called the program with TCP, I can create a TCP connection factory and put it into my factory variable, or I can also create a UDP connection factory object and put it into that variable. So these two classes are not related anymore, yet I can put objects of these classes into the same variable. So the benefit we had gotten before from the traditional implementation of this design pattern with the base class is something I can also achieve without having to use that class hierarchy. So let's go back to the connection class. It was all great that everything was working nice with the connection factories and without a base class, but I had temporarily introduced this base class again for the connections. Now the next step is how can we actually implement this design pattern without having to use a base class here? And can this be even done? All right, let's try. So I'm throwing away the base class of my connections. I just want to have a TCP connection, I want to have a UDP connection, no base class anymore. Okay, then I have to change my connection factories again. There is no std unique pointer of connection I can return. The TCP connection factory will again return a TCP connection object, and the UDP connection factory will again return a UDP connection object. Everything is nicely separated, no class hierarchies, no base class, no virtual functions. Now I still have my factory variable here, where I want to be able to store either a TCP connection factory or a UDP connection factory. I still have my signature. I want to call these factories in a way that they give me a connection. But how do I do this now? I mean, without a base class. Now we can actually use the same trick as we have been using before with std function. Std function is something everyone is familiar with because it's provided by the standard library and we just use it without thinking much about it. But std function is based on something which is called type erasure. And it turns out there's a Boost library which allows us to create our own std function-like variables which are also based on type erasure. So when you think of what std function actually does, it allows you to put anything in a std function variable as long as certain criteria are met. That is, something needs to be invocable. You need to be able to call something like a function. With Boost type erasure, you can create a new type which requires you to meet different criteria. So for example, I could say, I want to have a type called connection, and when I use this type to create a variable, people can put something into this variable as long as it has a send function. and as long as it is copy constructible. This is very similar to what std function does. Std function says you can put anything into a variable of a std function type as long as it is callable. And Boost TypeFrasure is the library you can use if you want to create your own std function-like types based on type erasure. So it looks a bit funny, this code, right? Sometimes it looks a bit complicated when you use a Boost library. So just to go through that very, very quickly. So here I'm defining a type called connection. This is a type any, which is provided by the library Boost TypeFrasure. And any requires me to pass in the concepts, the criteria I want objects to meet later when I want to store them in a variable of a connection type. So I can pass in here a list of types, and any requires me to use here another class from Boost MPL. It's called Boost MPL Vector, and that class allows me to list a couple of types one after another. So this is really the concept, the criteria, which are important to me. So I'm using here something called hasSend, and then I pass the signature of that function in here. So hasSend again is something I create with a macro from Boost TypeFrasure. There are lots of ugly details I have to get familiar with, but again, it's actually rather simple. This macro hasSend means there needs to be a function, a member function called send. And this member function called send must have this signature. This matches exactly with the send function our connection classes provide. Right? When we call send, we pass in a string, and send doesn't have a return value when we want to send something through a connection. And this is another thing, Boost TypeFrasure copy constructible, which the library Boost TypeFrasure provides, which just means that a connection needs to be, well, copy constructible. Why does this matter? Well, if we go back one slide, here this thing returns, of course, an object by copy. So our connections all need to be copy constructible. So if I have now this connection type defined, I can create my std function here, my std function variable, and I can say you can store anything in this variable as long as it is callable and returns a connection. What is a connection? A connection is anything as long as it has a send function and is copy constructible. And that's great. That matches exactly what our TCP connection and UDP connection are. So with Boost TypeFrasure, you can create your own std function-like types. Now, if you remember, a couple of slides ago, I told you I'm going to change the connection factories and remove the make function and turn the make function into an overloaded function operator. This was the trick I needed to go through in order to use std function. Now that we have learned that we can use Boost TypeFrasure, we can actually go back again and use make with our connection factories. So now when we create a connection factory and we want to store it in a factory variable, the question is again, what is the type of our factory variable? I just wrote there the type is connection factory, but we don't see any connection factory class here in our program. And again, we don't have any base classes. So back to Boost TypeFrasure. We just use that library to define here our connection type. Well, now we can use the library also to define our connection factory type. What is a connection factory? A connection factory is anything which has a make function with this signature. A connection factory also needs to be copy constructible so that I can copy this stuff around. And I'm using something Boost TypeFrasure calls relaxed, which means that I can create an object of this connection factory which can be empty, which I don't need to use immediately to store something inside. So this line on the right side where I create the factory variable without putting a TCP connection factory or a UDP connection factory right there into it. It's possible because I used relaxed here. Otherwise, the compiler would complain and say you can't have a variable where you don't put anything in. So with Boost TypeFrasure, I can get also the benefits I was getting before in my traditional implementation with these base classes and these class hierarchies. Are we done? Kind of. So all the advantages we have seen before, we got again, but we have a radically different implementation. There are 2 more slides I have for you when it comes to C++ code. There is actually a Boost library you could use for this design pattern. It's called Boost Factory. It actually has a slightly longer name. I think it's called Boost Functional Factory. So if you find this all too complicated with Boost TypeFrasure, you can actually turn to that library. Just to explain you quickly how to use it, this library has a class called Factory, and I use this class to define my TCP connection factory here. Boost Factory is a template you have to pass a pointer to. So I'm telling Boost Factory here that my TCP connection factory should return a pointer to a TCP connection. Why a pointer? Because Boost Factory creates that object with new. I do the same thing with the UDP connection factory. And then, of course, I have to change my send function, because when I call now the connection factory, I get a pointer to that connection factory. And as we have also discussed before, I, of course, need to call delete to delete that object again. If you don't like that, because we have again here this pointer semantics, there's also another class provided by this library, which is called value factory. So here I don't get a pointer to something created on the heap, but value factory just gives me the value directly. So I can go back to the previous implementation of send. When I call the connection factory here, I just get an object of the connection, and I can just use that object without having to worry of calling delete somewhere. So after having played now around with this design pattern quite a lot, let's think back about what this talk is about. So what's so world-class about it, or where was now the world-class code we were all expecting to see? So if we just think about it, what we were doing all the time, we were breaking down the requirements and constraints of the design pattern. So we were not just taking the design pattern as is and implement it as one big thing. We were really going through all the advantages the design pattern promises us. And if you remember what we did in the beginning, we were, for example, thinking about delegation and said, yeah, all we need for delegation is a function. We don't need the rest of it. So we were really making clear to ourselves what those requirements and constraints are, and we were trying to separate them. And in the second step, we were trying to use the features C++ provides us and libraries provide us to implement all these requirements and constraints which we broke down one by one. So all this tight coupling which you were getting with the traditional implementation, we were trying to break down into separate pieces, not just conceptually, but also in code. So yeah, why we did this? We were trying to get more expressive code, less ambiguous code, loose coupling. I don't like it that much if I phrase it like this, because expressive code, less ambiguous code, loose coupling, everybody always says, yeah, that's exactly what I'm doing. We don't need to talk about it. So what were we really trying to do? We were actually trying to reveal the meaning, our intention through code in a way that somebody who is going to read that code can really understand what the requirements and constraints are. So obviously, all that stuff which we have seen in the later slides, you also find in the traditional implementation of this design pattern. But there it's one big thing. If I break it down into separate pieces, like a function here, a template there, then some type erasure with Boost TypeFrasure, then it's very easy for me as a reader to understand that these things you all introduced because you all need them. with the traditional implementation, with the class hierarchy, you get maybe extra stuff which you don't want. Maybe you only want delegation, but you didn't know how to express this. So you get a lot of other things, and I, as a reader, I do not immediately understand what your requirements and constraints are. So if you are able to break this down, the concepts, and if you're able to express these separate concepts in code, you help me as a reader to understand what your requirements and constraints are and what you are actually trying to do in code. How did we do this in the end? Well, it's not something you can, of course, do overnight. It requires you to understand C++. You need to understand what the different features in the programming language are, why you would want to use them. The trick with type erasure is maybe something lots of people have never seen before. Stud function is something I think a lot of people are familiar with, but that you can use this one Boost library to create your own stud function-like types is maybe something new. So you obviously need to get familiar with the language, you need to get familiar with the tools, but maybe my talk helps a little bit to dive more into both the language and the libraries. But maybe you don't believe me. Maybe you say, okay, that's just one guy here talking about world-class code. There are a few more quotes which I found on the internet, what other people say. Well, obviously, I'm referring here to the Boost factory documentation. The reason why Boost has this library to make it easier to use this design pattern is because other people said already there's just too much boilerplate code if you implement all of that yourself in the traditional way. Then there's another talk from Sean Parent where he specifically talks about runtime polymorphism, something you can watch on Google. The entire talk is about having that goal in mind of not using inheritance. If you think of all the slides I went through, I was also not using inheritance in the end anymore. All the benefits I was getting through inheritance before, I could get through Boost type erasure. And the Boost type erasure documentation has also some interesting points. Here, for example, it says that C++ has two distinct kinds of polymorphism. There's virtual functions, a lot of people are familiar with, a lot of people kind of use by default, but there are other things, there are templates, and then there is, of course, that stuff which is introduced by Boost type erasure. We are at the end of this talk. Thank you for my attention. If you want to see whether all that code actually compiles, which I was showing you, you can find all of this on GitHub.